All right. So, chapter 14 is all about analyzing the quantitative data. Um, so, there's two preliminary sections that lay the foundations for studying statistics. So, first is to discuss the role of statistics in the research process, returning to themes and techniques that you already know. In the second preliminary section, the textbook outlines the process of acquiring data for statistical analysis. In the rest of the chapter, it explains and describes the distribution of single variables and the relationships among variables. Ethical issues are related to data analysis is examined. And this chapter should be successful if it encourages you to see statistics responsibly and evaluate them critically, and gives you the confidence necessary to seek opportunities for extending your statistical knowledge. This chapter does focus primarily on the use of statistics for descriptive purposes. So just to let you know that that's its focus. So this chapter introduces several common statistics in social research and highlights the factors that must be considered in using and interpreting statistics. Think of it as more of a review of fundamental social statistics, if you've already studied them, or as an introductory overview if you have not studied them. Statistics plays a key role in achieving valid research results in terms of measurement, causal validity, and generalizability. Statistics can include the following: frequency distributions, which is numerical displays that show the numbers of cases and usually the percentage of cases, the relative frequencies corresponding to each value or group of values of a variable. Cross-tabulation, or crosstab for short, is a bivariate of two variables. This distribution shows the distribution of one variable for each category of another variable. And then descriptive statistics, which is used to describe the distribution and relationship among variables. Inferential statistics is a mathematical tool that estimates how likely it is that a statistical result based on data from a random sample is representative of the population for which the sample is assumed to have been selected. So when we prepare for data analysis, we need to examine the quantitative data that needs to be prepared in a format that's suitable for computer entry. After the data is entered, they must be checked carefully for errors. This is a process that we call data cleaning. So we look for errors of the information that has already been entered into a computer file. So the first step in data analysis is usually to display the variations in each variable of the interest in what we call the univariate frequency distributions. These frequency distributions and graphs of frequency distributions are the two most popular approaches for displaying variation. Both allow the analyst to display the distribution of cases across the value categories of a variable. It also shows how cases are distributed across the values of the variable. There's three features of the shape of a distribution that are important. We have central tendency variability and skewness, which is a lack of symmetry. Central tendency is a feature of a variable's distribution referring to the value or values around which cases tend to center. The variability, which is a feature of a variable's distribution, this refers to the extent to which cases are spread out through the distribution or clustered in just one location. And then we have skewness, which is a feature of a variable's distribution, referring to the extent to which cases are clustered more at one or the other end of the distribution rather than around the middle. A variable's level of measurement is the most important determinant of the appropriateness of particular statistics. For example, we can't talk about skewness or lack of symmetry of a qualitative variable that's measured at the nominal level. Graphs can be easy to read. They very nicely highlight a distribution's shape, but if they're misused, they can distort rather than display the shape of a distribution. A bar chart is a graphic for qualitative variables in which the variable's distribution is displayed with solid bars that's separated by spaces. This includes percentages and modes. A percentage is a relative frequency that's computed by dividing the frequency of cases in a particular category by the total number of cases, and then you multiply by 100. The mode is the most frequent value in a distribution, also termed the probability of average. The histogram is a graphic for quantitative variables in which the variable's distribution is displayed with adjacent bars. So these are positively and negatively skewed. Positively skewed describes a distribution in which the cases cluster to the left, and the right tail of the distribution is longer than the left. If it's negatively skewed, then the distribution in which cases cluster to the right side, and the left tail of the distribution is longer than the right. Frequency distributions displays the number or the percentage, the relative frequencies, or both for cases corresponding to each of a variable's values or a group of values. The components of the frequency distribution should be clearly labeled with a title, a stub, which is labels for the values of the variable, a caption, this identifies whether the distribution includes frequencies, percentages, or both, and perhaps the number of missing cases. If percentages are presented rather than frequencies, some or both are included. The total number of cases in the distribution would be the base, or n, should be indicated. Remember that a percentage is simply a relative frequency. A percentage shows the frequency of a given value relative to the total number of cases times 100. And then if you look at Exhibit 14.6 in your textbook, you'll see what I'm referring to with the base n. Base n is the total number of cases in a distribution. The ungrouped data, this is continuous variables that have a large number of values. And because of this, it may be difficult to get a good sense of the distribution of the cases. The problem is that there's too many values to easily comprehend. So it would be nice if we could simply simplify distributions like these that we have a large number of different values. We can construct what's called a grouped frequency distribution. And so this is where the data is organized into two categories, either because there are more values and can be easily displayed, or because the distribution of the variables will be clearer or more meaningful. So there's many frequency distributions and many graphs that require grouping of some values after data is collected. There's two reasons that we do grouping. There's more than 15 to 20 values to begin with, a number that's too large to be displayed in an easily readable table, or the distribution of the variable will be clearer or more meaningful if some of the values are combined. Once we decide to group values or categories, we have to be sure that we're doing so so that we do not distort the distribution. So we need to adhere to the following guidelines for combining values in a frequency distribution to prevent problems. Categories should be logically defensible and preserve the distribution's shape. Categories should be mutually exclusive and exhaustive, so every case is classifiable in one and only one category. The first interval must contain the lowest value, and the last interval must contain the highest value in the distribution. Each interval with the number of values that fall within each interval should be the same size. There should be between 7 and 13 intervals. This is a tough rule to follow. The key is to not have so many intervals that your data are clumped or clustered into only a few intervals. You'll lose too much information about your distribution. And not to have so many intervals that the data are not much clearer than an ungrouped frequency distribution. And then we have steps that we need to follow for grouping data. We need to determine the number of intervals you think you want, decide on the width of the interval, make your first interval so that the lowest value falls into it. And then after your first interval is determined, the next intervals are a little easier to follow. Count the number of frequency of cases that appear in each interval and the percentage of the total. Yeah. Count the number or frequency of cases that appear in each interval and their percentage of total. So in summary statistics, sometimes called descriptive statistics, we focus on attention on particular aspects of a distribution and facilitate comparison among distributions. One way to interpret your data for your audience would be to provide a summary measure that indicates what the average violent crime rate is in the large U.S. cities. That's the purpose of the set of summary statistics called measures of central tendency. You'd also want to provide another summary measure that shows the variability in your data. In other words, a measure that shows how different the scores are from each other or from the central tendency. That's the purpose of the set of summary statistics called measures of variation or dispersion. So measures of central tendency is the most frequent value, or mode is the most frequent value in a distribution, right? So mode's our first one here. The variable distribution that has one case or interval that occurs more often than others is called a unimodal distribution. The distribution has more than one mode because there's two values that have the highest frequency is called bimodal. So a bimodal distribution has two non-adjacent categories with the same number of cases, and these cases have more cases than any other categories do. And then we have the median, which is the score in the middle of a rank ordered distribution. So the position average, or the point that divides a distribution in the half, the 50th percentile. The median is inappropriate for the variables measured at the nominal level. To determine the median, you first have to rank the orders in value from lowest to highest, then find the position of the median using the formula n plus 1/2. And then there's the mean, or the arithmetic average of all scores in a distribution. The arithmetic or weighted average is computed by adding up the value of all the cases and dividing the total number of cases. The mean is simply the arithmetic average of all scores in distribution. It's computed, like I said, by taking the value of all cases and adding and dividing by the total. So you have to take into account the value of each case in the distribution. The mean is equal to the sum of all values divided by the number of cases. If we're trying to determine if something is a median or mean, we use both, which are used to summarize the central tendency of quantitative variables, but their suitability for a particular application must be carefully assessed. The key issues to be considered in this assessment are the variable's level of measurement, or the shape of its distribution, and the purpose of the statistical summary. The shape of a variable's distribution should also be taken into account when deciding whether to use the median or the mean. Then we have the measures of variation, or the range, the true upper limit in a distribution minus the true lower limit, or the highest rounded value minus the lowest rounded value plus 1. The range can be drastically altered by just one exceptionally high or low value, which is called an outlier. The outlier, like I said, is extremely high or low. It's away from the rest of the cluster of the numbers that you find. The interquartile. So this avoids the problem that's created by unusually high or low scores in a distribution. The interquartile range is a distribution between the end of the first quartile and the beginning of the third quartile. It's the difference between the scores at the end of the first and third quartiles. Quartiles are the points in a distribution corresponding to the following, like the first 25% of cases, 50%, 75% of cases. Quartiles are the points in a distribution corresponding to the first 25% of the cases, 50% of the cases, or you could say the top 25% of the cases. So a variance is a statistic measure that measures the variability of a distribution as the average squared deviation of each score from the mean of all scores. It takes into account the amount by which each case differs from the mean. The standard deviation is the square root of the average squared deviation of each case from the mean. It has mathematical properties that make it the preferred measure of variability in many cases. When we look at cross-tabulating variables, this displays the distribution of one variable for each category of another. This can also be known as the bivariate distribution. And then we look at marginal distributions. This is a summary of distributions in the margins of a cross-tabulation that correspond to the frequency distribution of the row variable and the column variable. So this cross-tabulation reveals four aspects of the association between two variables. We have the existence. So do the percentage distributions vary at all among categories of the independent variable? And then we have the strength. How much do the percentage distributions vary among categories of the independent variable? And then we have direction. So for quantitative variables, do values on the dependent variable tend to increase or decrease with an increase in value of the independent variable? And then pattern. So for quantitative variables, are changes in their percentage distribution of the dependent variable fairly regular? Are they simply increasing or decreasing? Or do they vary? Perhaps increasing, then decreasing, or perhaps gradually increasing and then rapidly increasing. So in this monotomic relationship, it's a pattern of association in which the value of cases on one variable increases or decreases fairly regularly across the categories of another. And we look at the measures of association as a type of descriptive statistics that summarizes the strengths of an association. And then there's a gamma, which is a measure of association, sometimes used in cross-tabular analyses between two or more variables in a cross-tabulation. And then we have statistical significance. This is a relationship that's not likely to be due to chance. It's judged by a criterion set by the analyst, often that the probability is less than 5 out of 100, or p is less than 0.05. So cross-tabulation can be used to study the relationship between two variables while controlling for other variables. So we'll focus our attention on controlling for a third variable in this section, but we'll try and say a little bit about controlling for more variables at the section's end, if you read in your textbook. So there's three different types for variable cross-tabulation. Identifying an intervening variable, testing a relationship for spuriousness, and specifying the conditions for a relationship. When we look at elaboration analysis, the process of introducing a third variable into an analysis in order to understand or to elaborate the bivariate two variables relationship under consideration, we look at an additional control variable that can also be introduced. Intervening variables are variables that intervene in the relationship between two variables. Example, there's a parental supervision that intervenes in the relationship between gender and delinquency. And then we have subtables. These tables describe the relationship between the two variables within the discrete categories of one or more of the other control variables. Our extraneous variables, another reason for introducing a third variable into a bivariate relationship is to see whether the original relationship is spurious due to the influence of the extraneous variable. A variable that influences both the independent and dependent variables so as to create a spurious association between them that disappears when the extraneous variable is controlled. In other words, the only reason the independent and dependent variables are related is that they both are the effects of a common cause, another independent variable. And then specification, we look at by adding a third variable to an evaluation of a bivariate relationship. The data analysis can also specify the conditions under which the bivariate relationship occurs. So specification is a type of relationship that involves three or more variables in which the association between the independent and dependent variables varies across the categories of one or more other control variables. So by introducing you to cross-tabulation, hopefully it's helped you to think about the associations among variables and to give you a relatively easy tool for describing associations. A regression analysis here is a statistical technique that's for characterizing the pattern of a relationship between two quantitative variables in terms of a linear equation and for summarizing the strength of this relationship. Note that a multiple regression analysis is where you could test to see whether several variables have independent effects on a dependent variable after statistically controlling each other. So are there other variables in addition to poverty associated simultaneously with the murder rate? Would be an example. Correlation analysis is a standardized statistical technique that summarizes the strength of a relationship between two quantitative variables in terms of its adherence to a linear pattern. So how well does the regression line fit the points? In other words, how close does the regression line come to the points, right? So actually it's the square of the vertical distance on the y-axis between the points and the regression line that is used as the criterion. The correlation coefficient, also called Pearson's R, or just R, gives one answer to that question. A correlation coefficient is a summary statistic that varies from 0 to 1 or -1, with 0 indicating the absence of a linear relationship between two quantitative variables, and 1 or -1 indicating that the relationship is completely described by the line representing the regression of the dependent variable on the independent variable. And to look at things from an ethical standpoint, we need to know how not to lie about the relationships and basically just give the facts and what the data says that we collected. It can be very tempting to search around in the data until you find something interesting that emerges, but that would not be ethical. A reasonable balance must be struck between deductive data analysis to test hypotheses and inductive analysis to explore patterns in a data set. That helps to keep everything above board and following ethical guidelines.